We will now continue with our next slot. There's a few more to come, which is about how to predict financial crashes, maybe in a nutshell. And here it's exactly about the question, how can we translate the financial crash problem, so I was told there is, to a near-term quantum computer. That sounds very interesting, going back to the financial domain now here. With me is Ben Niehoff, who is a quantum software engineer with Parity Quantum Computing. Mr. Niehoff, welcome. The floor is yours.
Yeah, thank you. Yes, just getting the presentation up. Right, so first of all, thank you very much for the invitation to speak. It's been a very nice conference so far. I learned very many interesting things. So yes, this is about how the parity architecture can help predict financial crashes. So this will be a little bit on the technical side, but hopefully it shouldn't be hard to follow. I'm going to begin by simply telling you what the parity architecture is and why it's useful. And then I'll describe what this financial crash problem is, and then, of course, how one of these helps the other. So, of course, the theme of this conference is real-world use cases, and quantum optimization is a major part of that. There are many interesting problems that one wants to solve in various industries regarding, for example, electronic structure or scheduling or protein folding. We've heard a whole lot of other examples the last 2 days. And of course, the general goal in each of these cases is to find the best solution to a problem out of many possible solutions. And the way we do this on a quantum computer, or in particular a quantum annealing sort of device, is that we assign all of these configurations some energy. So we write down a Hamiltonian that represents the cost function of this optimization that we want to solve. And if we're lucky with what this Hamiltonian looks like, we can then put it on a quantum computer and use various methods to find the ground state. Of course, the interesting question is what happens when we're not lucky. So what can we do about the form of this Hamiltonian to make it possible to encode on computers? So this is kind of where the parity architecture comes in. One of the most common ways to encode problems is this formalism called Cubo, which stands for quadratic unconstrained binary optimization. So what you do in this case is your Hamiltonian is generically some polynomial in a whole bunch of logical variables. And this Cubo transformation is the way of for example, if your Hamiltonian has higher degree terms in this polynomial, for example, the one in this picture has some third order terms, then what you do is you add some ancilla variables to break up these terms into quadratic terms. And once everything is quadratic, you can map it onto all sorts of devices that implement pairwise couplings between qubits. What we have is a completely different way of approaching this problem. And so we're describing this as HCBO, which is higher order constrained optimization problems. So of course, generically, problems don't just magically fit into Cubo. They will have these higher order terms that you need to deal with. And the parity architecture is a way of approaching that without doing a Cubo transformation. It's a different technique of encoding the problem. But we also have ways of dealing with constraints, which will not really come up with in the financial crash problem I'm talking about today, but is very interesting for a wide variety of other problems in the industry. So as far as what the parity transformation is, right, so as a sort of toy example, I'm giving you a problem that already has only two-body interactions. So this represents some graph theory problem where these two-body interactions are things to find on the edges of some graph. So you may be using this to calculate minimal networks of some kind or max cut or something like that. But the point is that we start with this problem Hamiltonian and we completely rewrite it into a physical Hamiltonian. And what happens is that every interaction term in the original Hamiltonian becomes a single local degree of freedom. And what's nice about this is that now the original problem is now encoded only in local fields acting on a single qubit, which is much nicer to deal with than other sorts of complicated things. there's a redefinition of variables that happens in order to do this. And as a consequence of that redefinition of variables, one also introduces a lot of constraints. And these constraints are these four-body terms that will act along plaquettes in some sort of grid layout. But the point is that this initial Hamiltonian can be basically arbitrary. And what you end up with at the end is this physical Hamiltonian that is all phrased in terms of local interactions on a two-dimensional device. You have local fields that implement the original couplings that define the problem. And then these constraint terms, this is a four-body plaquette, but it still acts only locally. It doesn't have to reach across the chip somewhere else. And what's nice about this, of course, is that you can now realize arbitrary problems on realistic devices and without too much overhead. So how this transformation actually works. So what I do is I take every interaction in the original Hamiltonian and I map it onto some new physical degree of freedom. So I started with n logical degrees of freedom. And if I have a two-body Hamiltonian to begin with, then I have n choose two physical degrees of freedom after doing this. So I've increased my number of degrees of freedom, quadratically in this case. So then I have to add a number of constraints that enforce the fact that my new degrees of freedom represent the original problem. Okay. So there are, right. So the point is that the total number of degrees, the net number of degrees of freedom should be the same as it was originally. So I have these, if k is the number of terms, then I have k minus n constraints. So what are these things? Right. So constraints come from closed loops. If I'm talking about a graph, these are loops in some graph. As I told you, the edges of the graph represent couplings in the Hamiltonian. So these loops are closed loops you can draw in the graph. And the basic idea is that my new qubits represent products of spins. And these graphs, these closed loops represent consistency conditions. If I tell you that these three variables are equal to a product of these logical spins, these variables on the right, then if I give you the combination of all three of them, then there's the consistency condition, which is that they must multiply to 1. And you can say that each closed loop must have an even number of spins down because it's equal to a product of spins. And then these constraints that you write in terms of spin products, they become plaquettes. So the example I just gave was a three-body constraint. This becomes this triangular configuration. And this represents a term in my physical Hamiltonian that looks like this. And you can also write down a four-body constraint. This is a four-variable loop, and it becomes a square plaquette with a term that looks like this. These are the plaquettes that I showed you in the original drawing. So they can be laid out in this two-dimensional configuration. And as I told you, the original couplings are realized now as local fields. So that's how the original problem is encoded. And then what's nice about these plaquettes, each of these squares is a plaquette. The precise strength of the plaquette couplings is not important. This parameter CL in this physical Hamiltonian only needs to be large enough that it affects some constraint, but the precise value of it is not that important. So I've sort of given you this picture of how you can take a generic problem defined on some graph. So it's take some graph theory problem expressed as an Ising Hamiltonian, and you can always reinterpret this problem in terms of new variables that can be laid out in this sort of triangle. But of course, the parity architecture is a bit more generic than that. I was telling you we want to look at Hamiltonians with higher order terms. So in this case, you'd be looking at something that's a hypergraph. So if I have some Hamiltonian with k-body interactions, the example I've shown here has three-body interactions. So it has these three-body hyper edges that are highlighted in red and blue. And in order to deal with this sort of Hamiltonian, we use basically the same algebraic techniques. The interpretation in terms of closed loops in a graph is a bit more complicated. We're calling it a generalized closed cycle condition. But what it really means is this algebraic sort of manipulation. So the point is that for every term in this Hamiltonian, I'm going to define a physical spin, which is equal to the product of the logical spins. So here are the physical spins with a hat on them. And the point is, for example, this one, 3, 4, 5, has 3 indices, and it represents the product of these logical spins. And the particular 4 physical spins that I've written down here can be combined into a constraint that fits in this square plaquette. And the way that you find these constraints is a generalized cycle condition where you simply write down the product of these. And then if you expand them in terms of the original variables, you must get something trivial. The point in this case is that each index in this product appears an even number of times. So if that logical qubit is spin down, then I have an even number of -1 spins in the product. So I get 1 at the end. So this must be, in order for these physical spins to represent the original problem, then I must impose this constraint on the values. Right, and then what you do with this is you create similar pictures to the one I showed you of the triangle, but you can get very, very generic looking pictures with squares and triangles and all sorts of different orientations. Right, so this is sort of a picture of how you use the parity architecture on annealing devices. But another interesting approach to annealing type problems is the QAOA, the quantum approximate optimization algorithm. So this implements an annealing-like algorithm on a digital device, which typically does have these pairwise couplings. We're sort of imagining an abstract device here that implements local one-body gates and then also CNOT gates between neighboring sites. And the point is that all of these constraints I showed you as plaquettes in the earlier slides, you can actually interpret these as chains of CNOTs in a digital device for a QAOA implementation. And you can get layouts where you have these, all sorts of different Tetris-like shapes that fit together in basically arbitrary ways. But the main principle is the same, that you can lay out all these constraints such that they're local and implement arbitrary problems on a device with only local connectivity. So I mentioned you get these very interesting looking pictures, and here's sort of a gallery of all of these pictures. Here are some graph theory problems. If you compile hypergraph types of problems, you get very similar pictures with squares and triangles connecting between everything. Right. Good, so that's sort of the basic idea of what the parity architecture is and how it can help you implement problems. The main points to put together is that you can take an arbitrary Hamiltonian and do this change of variables and end up with a local Hamiltonian that you can put on a realistic device. So now, of course, there are many ways of taking some problem and putting it on a device. So how is this particularly helpful in financial crash problem, which I will talk about next. Right, so the financial crash problem is sort of a toy model of a financial network, and that was detailed in this paper at the bottom of the slide. So the point here is there are a number of financial institutions that own shares of assets, and these assets have some price, P, so P is a vector of asset prices, and V is some vector of values of these institutions. And these institutions can be connected in all sorts of complicated ways. So they own portions of the assets, but there's also some sort of graph of cross ownership between the institutions themselves. So this is represented by some collection of 3 matrices. So this matrix D talks about given some institution V, it gives you the proportion of ownership of all of the assets that institution possesses. And then there are 2 further matrices, this C twiddle and C. These represent the cross ownership between the institutions themselves and their self ownership. And what happens is you can write down this sort of this formula. This is a simple linear algebra problem, and the way I've described it so far is given given the asset prices, what are the values of the institution? This is very straightforward. Of course, this doesn't represent what real markets do. Real markets are not so simple. What happens when prices change? So these institutions, of course, have operating costs, so their value can't drop below some number. And then, of course, market players act according to their confidence in the market. What we've seen in historical market crashes is that people lose confidence. And when people lose confidence, they sell all of their holdings and institutions crash. So these are nonlinear effects that are not accounted for in this equation. We need to add them in. So what we do is we modify the model by adding this nonlinear function b, which is highlighted. So b takes the form that I've given here. There's some coefficient in front, and the interesting part of b is this step function contribution, which tells you that when the value of an institution drops below some critical value, you get a complete, that institution basically fails dramatically. This represents this complete loss of confidence in the institution. So now I add this term to the model and I ask, well, what's the equilibrium value now? If I manipulate the prices, what actually happens? And now this problem actually becomes difficult to model. You can put this through the more institutions and assets, of course, you have a more and more difficult problem. And the sort of situation you get is that things work fine for a while, then when the prices fall below some threshold, you get a whole bunch of things failing. So what we've done is we've translated this, okay, how to encode this problem on a quantum computer. What I do is expand this step function in terms of Legendre polynomials. So I ended up with some polynomial Hamiltonian. And now I have this higher degree polynomial, which is good for the parity architecture. So we do some sort of comparison between the parity architecture and, for example, Cubo. And this is what I have on the final slide. So what is plotted here is the number of C0 gates being used in the traditional gate model with Cubo versus the number of C0 gates in a digital parity compilation, and then finally versus the number of effective gates in an annealing local compilation. And you see here the obvious advantage of the parity architecture is it saves you, in this case, a constant factor of C0 gates. And it's a dramatic saving if you actually run this on an annealing device. So essentially you get this, you can get sort of constant depth implementations of arbitrarily large versions of the problem. Right. So thank you very much for your time, and I'll stop there.
All right, Mr. Niehoff, thank you so much for this. This was, I think, very eye-opening and interesting. We have one question from the audience, which I would like to read out to you. The question goes as follows. The background is their expertise is in error-correcting codes, both classical and quantum. So the parties, Mr. Niehoff, you are describing, remind them of parties that appear in error-correcting codes. Question, can error-correcting codes be used in this approach? This is the question.
Right. In fact, the parity mapping is a form of error-correcting code. It's a classical linear code. And this is detailed, and I didn't actually put the citation on one of these slides, but if you look at our website, we have some papers we published last year where one of these discusses this in a bit more detail.
All right, Mr. Niehoff, thank you for this. One more question from my side. I'm not an expert in this field, so my question will be a bit more generic, but I will put it anyway, which is looking into the path, looking onto the path of your research and your work there. Where could you see, like, how is the path to putting this into some kind of a concrete application even more? How do you see this journey in the future, going from the models and the mechanisms you described, even closer into kind of putting this into practice?
Right. I mean, I think this is very exciting. So, of course, Parity QC is involved in many of these German initiatives in partnerships with hardware companies to design machines. So some version of Parity architecture is being implemented at this moment in many of these projects. I think there's a very exciting future, especially as we get to machines of larger scales with more qubits. Of course, there's some qubit overhead in actually implementing the architecture, which I described, but we think overall it's less than transforming to Cubo. We think it's of course easier to manufacture devices. that only have local connectivity. So we think this is very exciting for the prospect of having very large devices and being able to encode arbitrary problems on them.
I see. Thank you so much. This sounds very promising. Thank you so much for being with us today. Thank you for sharing your insights. Mr. Niehoff, I wish you a great remaining conference, and would be happy to welcome you soon at some point. Thank you so much.
Yes. Thank you.